Assalamu alaikum. We are discussing the alternative approaches to the observer design, and this is the second method using this just matching the coefficients. So the system as it is, we represent with the existing system with the default representation it is into, and then with the desired characteristic equation, we just compare the values and figure out the values of the L1, L2, L3. So basically, we'll deal with one simple example. Example 12.9. A transfer function is given, g of s equal to 407 s plus 0.916 divided by s plus 1.27 into s plus 2.69. So this one has to be represented, as they said, in the phase variable. Phase variable. So in the phase variable, how can we design the observer? That is the thing, and also some other parameters related to the transient response are given. That is zeta equal to 0.7. Sometimes instead of zeta, they can also give percentage overshoot, and omega n, natural frequency, is given as 100. So let's try to solve it with in the phase variable form. So just if you multiply, then you will have something like this: 407s plus 372.81, 72.81 divided by s square plus 3.96s plus 3.42. So in the phase variable form, we know that our first phase, and the second phase is the rate of change of the first phase. So basically x1 dot equal to x2. So since we have only two second order system, so there will be two, x1 dot and x2 dot. So x1 dot is equal to x2. So based on that idea, we can easily directly write the A matrix, that is 0, 1, x1 dot equal to x2, and the x2 dot equal to the rest of the characteristic equations. So the coefficients that coming in the reverse order basically. So minus 3.42 minus 3.96. And what about our C matrix? C matrix is the output equation that is related here. So basically, this is the coefficient of x1, this is our constant, and this is a coefficient of x2 or s. So basically, in the reverse order, as we see, 372.81 and 407. So first thing is, after obtaining this one, or even before obtaining this one, you can also go for your representation. Okay, so signal flow representation, you need two integrated, and they're related. So one is just connected with another one, 1 by s, 1 by s, and now our output will give the name. So this is your x1, this is your x2, and this is your x2 dot. And our input is u, coming with again 1, and our output is 372.81 x1. So this is 372.81, and also we have gain that is coming from x2, and that is 407. And what about the feedbacks? So basically, both of them are going to x2 dot. So minus 3.96, and also this one from x1. So basically it will be minus 3.42. So this is our system. Now with this system, we have to go for designing the feedback. Okay, so feedback is basically from y minus y1. So our original y is this. Is it okay? So now if you have a replica of the actual system, replica of the actual system, okay, so this is our output coming, and this output is known as y hat. Is it okay? So from y, you should have another input. So basically what we are interested is y minus y hat. So with again 1, this is a scenario. So that point is actually your y minus y hat. Y minus y hat. So the rest of the thing will also be added. Okay, so 407, this is 372.81. And the other, this was your x2 hash hat, you have to give first, then you have to give dot. So it is coming from self feedback, that is minus 3.96, and the feedback from the other one, that is actually your x1 hat. This is your x2 hat with a gain of minus 3.42. So now from the feedback from y minus y hat will be getting to one will be going to x1 dot and the other will be going to x2 dot. So x1 dot is basically your x2 hat. So one of the feedback will be this one with L1 and the other will be this one with L2. So our objective is simply to find out what are the values of L1, L2. And if you want, you can also connect them, same input. So this is U with again 1. So this is your system. Okay, so now let us try to figure out the values of L1 and L2. So this is your signal flow graph. Definitely, since we have A and C metrics, we can find out OM, that is observability metrics, which will be C and CA. And we have to find out also the determinant of the observability metrics, and you have to prove that it is not 0. That means your rank of the system, rank has to be 2, which is the order of the system. Order of the system. So this is part of the designing that you have to do always. So next is finding the desired value, that is A minus LC. A is already figured out, which is 0, 1 minus 3.42 minus 3.96 and minus you have L1, L2 with 372.81 and 407. Okay, so this will give us, we're writing it quickly, skipping one line because if we have practiced well, it should not be. Actually, in this particular case, it's wiser to not skip. So let's try to do the whole thing. So 0, 1 minus 3.42. There will be more possibility of having error. So that is why we're writing in this way. So 372.81 L1, and you have 407 L1. Then 372.81 L2, then 407 L2. So now if you finally write the find the matrix, then what you're going to get is minus 372.81 L1, 1 minus 407 L1 is 3.42 minus, of course, plus 372.81 L2. And you have minus 3.96 plus 407 L2. Okay, so next thing is finding the desired characteristic equation. So now what do you have? Determinant of Si minus A, or also you can use the eigenvalue. So lambda I minus A minus LC equal to 0. So this time you cannot, you don't know how to write the characteristic equation by shortcut. So that is why you have to deal with the procedure. So there is, you have to find the determinant of lambda plus 372.81 L1 minus 1 minus 407 L1. And then you have 3.42 plus 372.81 L2 lambda plus 3.96 plus 407 L2. Okay, so cross multiply, simplify. So you're going to get lambda square plus 3.96 plus 372.81 L1 plus 407 L2 lambda plus 3.42 plus 84.39 L1 plus 372.81 L2. So this is your lambda square, some lambda term, then the constant term. And also we have been provided with zeta and omega n. So zeta is 0.7 and omega n is basically 100. So based on this value, we can also find out our characteristic equation. So lambda square plus twice zeta omega n lambda plus omega n square. So that this will give us lambda square plus 2 into 0.7 into 100 lambda plus 100 square. So basically what we're going to get is lambda square plus 140 lambda plus 10,000. Okay, so comparing these two equations, comparing this equation and this equation, we have to find out or equate the values of L1 and so we have equating the coefficients. Finally, we can figure out that L1 will be minus 38.397 and your L2 will be 35.506. So now these values you can just directly plug into the value with the phase signal flow graph that we had previously. So basically just replace the value here, that is minus 38.397 and this will be your 35.506. So this is how you have to go for designing the equation. As you can see, even with a second order system, the calculation is more complicated than it was done in the observer canonical form. So you can easily imagine what will be the scenario if the order is 3 or more. Okay, so that is why this method is not preferred for higher order system. Rather, converting the system into the observer canonical form, and then based on the design in the observer canonical form, the gains that L's you are going to get. So those L is again transmitted or transformed back to the original form. So that method is a lot easier, even though that is more dependent on our matrix manipulation, but on the calculations of this method is more complicated. So that is why we have to either choose in between the two, either complex matrix manipulation or the complex calculation that it comes in this method. Okay, so this is the end of this session.